Hello everyone. I am Dr. VIJAYA, Assistant Professor of Mathematics, Sri Sharada College for Women, Salem. Now I am going to take integral calculus. First, what is meant by integral calculus? Integral calculus is a branch of calculus that deals with the concept of integration. It involves finding the accumulation of quantities such as area, volume, mass over a continuous interval. Integral allows us to determine the total or net effect of a continuous process by summing of some infinitesimal quantities. See the picture. Here we take the quantity within the limit a to b. Here we split into sub-intervals and then summing of the intervals, we get the total area of the process, total area. This is called integral calculus. What is the goal of the integral calculus? The primary goals of integral calculus include determining the accumulation of quantities over intervals, finding antiderivatives or indefinite integrals, solving problems related to area, volume, and other physical quantities. Next, we are going to see the history of integration. Archimedes is the founder of the surface areas and volumes of solids such as sphere and cone. His integration method was very modern since he did not have algebra or decimal representation of numbers. Then Gauss was the first to make graphs of integrals, and with others continuing to apply integrals in mathematical and physical sciences. First, we see in the 17th century, Isaac Newton and Wilhelm Leibniz independently developed modern integral calculus, introducing the fundamental concepts and techniques that we still use today. This is the history of the integration. Next, we are going to see the applications to real world. Integration was used to design the Pynchon towers, making it stronger. The first diagram shows the Pynchon towers to make it stronger. And the second picture shows the Sydney Opera House. Many integral equations were used in designing of this opera house. And the third picture shows that the finding the volume of wine cask was one of the first uses of integration. So these are the live applications of integrations to real world. Next, other uses of integral calculus. Finding areas under curved surfaces, center of mass, displacement, and velocity and fluid flow are the other uses of integral calculus. It plays a crucial role in various fields of science, engineering, economics, and beyond. Also, it is used to solve problems involving continuous change such as calculating areas under curves, determining volumes of irregular shapes, especially not for regular shapes. Irregular shapes also used to determine here. Finding center of mass, analyzing rates of change in physical and economical systems. These are the other uses of integral calculus. Next, we are going to see what is meant by integration. Integration is nothing but it is the process of evaluating an indefinite integral or a definite integral. The indefinite integral f of x dx is defined as a function g such as and its derivative integration over dx g of x dx equals to f of x. Next, definite integral. Integration over a to b f of x dx is a number whose value depends on the function f and the numbers a and b, and it's defined as the limit of a Riemann sum. Indefinite integral involves an arbitrary constant, for instance, x squared dx equals to x cubed plus c. So here we integrate x squared dx. The answer result is x cubed plus c. The arbitrary constant c is called a constant of integration. Next, we are going to see why we include the constant c. C represents for constant. Why we include constant c in all the integration? Let's now see. The derivative of a constant is 0. However, when you integrate, you should consider that there is a possible constant involved. But we don't what is it for a particular problem. Therefore, we can just use c to represent the value. To solve for C, you will be given a problem that gives you the value of y of 0 equal to 0. Then you can plug the 0 in for x and y of 0 the value for y. So the remaining parts of the integration that cannot be integrated, we use the constant for C. So always we use constant adding to the integration parts. Next, power rule. Integration over u power n du equals to, the formula is u power n plus 1 divided by n plus 1 plus constant C. Here C represents the constant of integration. U is some function, n is power, du is the derivative. This is the basic formula for integration, and some trigonometric substitution formulas are here given. These are the trigonometric formulas we are using in the integration. Now, we are going to see the integration by parts. Start with the integration by parts means we can't directly integrate the function. Suppose the function is given in the product rule that we cannot directly solve, that we cannot easily directly to solve, then we use integration by parts. Let's see the integration by parts. Start with the product rule. D by dx uv equals to u dv by dx plus v du by dx. Here we cancel the derivatives. Then we get d of uv equals to u dv plus v du. Next, we take the right hand side of the v du to the left hand side. U dv as it is, the differentiation of u v minus v du. Then we apply the integration parts. We get u dv as it is, and integration of d into vu becomes uv, and the formula v du is. So integration by formula parts is u integration over u dv equals to uv minus integral v du. This is the basic formula for integration by parts. Next, what is meant by u here? U differentiate to 0 usually. dv is easy to integrate. This is the any function that differentiate to 0 usually. We take it as like this. And dv is easy to integrate. So if we can take it like this, it is easy to integrate easily. The integration by parts formula is a product rule for integration. Choose u is this order. Lippert. What is meant by Lippert? L stands for logs, I stands for inverse trigonometric function, P stands for polynomial function, E stands for exponential function, T stands for trigonometric function. If we choose the u in this order, then we can easily integrate. If the u is given in the mixing of these orders, we choose this order, then we can easily integrate the functions. Next, for example, if we are taking the integration x cos x dx, already we know the formula. Integration by parts formula is u dv equal to uv minus integral v du. We take the format of logarithmic functions, inverse trigonometric function, polynomial function, exponential function, and trigonometric function. First here x cos x given. So polynomial factor, we in this order, first polynomial here given is polynomial function and trigonometric function is given. So in this order, we take first polynomial factor, because logarithmic and inverse and trigonometric function is not given. So we choose in the third order that polynomial factor. So we can choose is x, polynomial factor u equal to x. So then differentiate du equal to dx. Then b dv equal to cos x dx. Remaining term, integration of cos x is b equals to sin x. Then apply in the formula. U equal to x, v equal to sin x minus integration over v sin x du equal to dx. X sin x as it is, we can easily, sin x, the integration is minus cos x. Already we are having minus. So minus into minus plus. So x sin x plus cos x, and the integration constant c. So this is the basic problem for using integration by parts. Next, we see the logarithmic factor. First one. Okay. So here log x dx taken as log x as u, dv equal to dx, du differentiation of log x is 1 by x, b equal to x. So then applying the formula log x plus x integration over x du equals 1 by x into dx, x log x minus x cancel. So integration of dx is x and the integration constant c. Next we see other examples. X squared e power x dx. Here polynomial function and exponential function are there. So first see we take it as polynomial function, and then for Lipid formula polynomial function, and then trigonometric function is last one. Okay, u equal to x squared, then differentiate. If we differentiate x squared, then it becomes differentiation of x squared is 2x into dx, dv equal to e power x into dx, integration of dv equal to b equals to e power x. Then here apply u is x squared, b e power x minus integration b is e power x, du is 2x dx. Here x squared e power x is as it is, 2 is the constant, so taken outside. Remaining term is x e power x. Again here polynomial function and trigonometry function we are having. So again we have to integrate this function as integration by parts. So let us take this function only. So here u equal to x in the same order polynomial and trigonometric. So u equal to x, dv equal to e power x dx. So differentiate with respect to x, du equal to dx, integration with respect to x, dv equal to e power x dx, integration e power x. Then we substitute in the formula x squared e power x as it is, minus as it is, 2 as it is. Here we apply uv minus integral v du for this function. So x e power x minus e power x dx, x squared e power x as it is, minus 2 x e power x as it is. Here integration of e power x is this 2, minus into minus plus 2 e power x, integration of e power x is e power x plus the integration constant c. Last two problems we have seen only one time integration by parts, but here we are using this as one time, and second time we use integration by parts. So 2 times here we are using integration by parts. Next, e power x cos x. Here exponential function and a trigonometric function. So in this order we are taking exponential function as u and the trigonometric function as here. So these are the integrations we are using here. See, this is for our example workout. Again here these are few examples for workout. This is also solving the unknown integral. So it works when both factors integrate and differentiate forever. So these are some of the examples we can integrate. Next, a shortcut tabular integration. Tabular integration works for integrals of the form f of x is the g of x into dx, where differentiates to 0 in several steps. Integration repeatedly. If the function gives f of x we taken as differentiate to 0 and g of x we choose as integration repeatedly. We see the few examples for this. X squared e power x. F of x is the derivative, goes to the 0. And e power x integration is again and again, integration is e power x only. Compare this problem with the same problem in other way. Okay, x squared, differentiation of 2x. Next to 2, 0. These are the differentiation. These are the this one, integration. So x squared e power x is x squared e power x minus 2x e power x minus 2 e power x plus 0 into e power x is 0. So you will put c. This is the one of the easy way by choosing the integration. Same problem we are taking here as the integration by parts. Here see x squared e power x dx, f of x chosen as derivative, g of x as integration. The same problem taken as for integration by parts. Taking as integration by parts, u equal to x squared, dv equal to e power x. Applying this, again integration by parts. This is same answer. X squared e power x, 2x e power x plus 2 e power x plus c. X squared e power, same problem. This is easier and quicker with a tabular integration. Some of the problem is quicker. Tabular integration is quick, too easy to solve. Next, same problem, tabular format. Okay, if we develop the formula by considering how to differentiate products, you suppose y equal to uv, then dy by dx equal to v du by dx plus u dv by dx, where u and v are both functions of x. Suppose we are taking here as both functions of x, we integration by this one method. Integration, we are using the, can you see, has to how integration with the product. X sin x, here is the product. The function has to integration of the left hand side is a product, but one of the right hand side is a simple function that we can integrate easily. Here are some of the examples. Okay, next we take x dx by dx sin x plus x cos x, generalization formula. Next we are saying x cos x u dv by dx equals to uv minus integral du by dx. These are the some examples. Next, integration by parts. To integrate some products, we can easily use the product integral u dv by dx into dx equals to uv minus integration over d du by dx into dx. Here we are using, this is the function of some f of x and g of x. We can use this formula. So using this formula that we differentiate one factor u to get du by dx, here, this one. Next, using this formula that we differentiate one factor as du by dx and the integrating factor from the dv by dx to get v. Using this formula, we have to integrate this one dv to get v. For example, if we are taking integration over 2x sin x dx. Suppose we are taking u equal to 2x and dv by dx as sin x. Differentiate with respect to x 2 and integration with respect to x sin x, different integration of sin x is minus cos x plus c comes later. Have you substituted the second formula? Notice the first term uv is completed, but the second term is still need to be integrated. See this. So same problem still continues. Here we are taking the differentiation. Already we see in the last slide. 2x dx sin x dx u dv by dx equals to uv minus v du by dx. So here applying this minus 2x cos x plus minus into minus plus 2 cos x minus 2x cos x plus integration of 2 cos x is 2 sin x plus integration constant. The second term needs to be integrating. So this is the answer for integration over 2x sin x dx equals to minus 2x cos x plus 2 sin x plus c. Again, we see second example, x squared e power 2x. Like this, we have to integrate and substitute in the formula. We get the answer. Next, we see the simple problems for the exercise, for our exercise. X e power x dx plus x cos x 3x. These are the integration formula for our exercise. Definite integration by parts. Some of the, then applying the limit. Okay, so here integration by parts is over. Last we see. Next integration limit is 0 to 1. Then we substitute for the upper limit first. Minus of lower limit gives 0. Lower limit e power 0 is 1. Minus 1 minus into minus plus 1. Integration by parts cannot be used for every product. It works if we can integrate one factor for the product. The integration of the RHS is easier than when we started with. This is an exception, but you need to learn the general rule. These are some of the examples. Using integration by parts, e power x sin x dx, e power sin x dx. This problem continues here. Next, second problem, x squared sin x dx. Limit integration over limits 1 to 2 log x sin x. These are some of the applications of this, the important application of integration by parts. Now, any suggestion, any questions you may ask? Integration by parts is we are clearly see. Okay, thank you.